Right, question 11, the guitar equation and the guitar question. Right, it's standing waves, but again, you're not going to see easier than this, to be honest, in an A level or AS paper, to be honest. Yeah, standing waves, right, we've got a guitar. When it's plucked, the standing waves set up. When you pluck a guitar, the note you hear is of the fundamental. Right, 6 marks. Explain how a standing wave is set up on a string. This has to be the easiest 6 mark question I've ever seen in an A level. This is the standard description of a standing wave on a string. Okay. Now, this is quite a neat little maths tool here where we can. This just basically adds two waves together. Right. So how a standing wave set up on a string? Well, you have two progressive waves traveling in opposite directions. They have to be the same frequency, the same wavelength, preferably the same amplitude. And what they do, they superpose. They superpose and interfere with each other to produce a resultant standing wave. So there's one of the progressives going down the string. The reason we have two progressives going in opposite directions is because the string is fixed at each end, so we get reflection. Okay, so if I show the reflected wave in blue, we can see the two waves are the same wavelength, traveling in opposite directions at the same speed, and in this case, they've got exactly the same amplitude. Now, if we add these together, we see the resultant standing wave. Okay, so another feature in the mark scheme, it said you could describe that when the two progressive waves are in phase, when they're momentarily in phase with each other, we get maximum constructive interference. So the resultant standing wave is at its maximum. When the two progressive waves a short time later are in completely antiphase, 180 degrees out of phase, that's when we get total destructive interference. Okay, so like I said, that has to be 6 marks in the bag for everyone. All right, you need to learn those definitions. That's just a standard recall question. Okay, but quite a nice little maths tool. This, I like this. Anyway, back to the question. Even the part where a thicker string produces a note with a lower fundamental frequency than the thinner string of the same material. Justify this statement. Okay, well, what's the equation for the velocity? The velocity of the progressive waves on the string is root t over mu. Okay, if you remember, t is obviously the tension in newtons, and mu is the mass per unit length, which is kilograms per meter. Standard units there. That will give you the velocity of the progressive waves in meters per second. Okay, but we also know the wave equation, don't we? V equals f lambda. Okay, for the these are the stats for the two progressive waves. We just equate the v's there. So if you equate the v's, we've got f lambda equals root t over mu. Right. Now all we're doing here is we're producing a thicker string. So it's the same length, so it's going to have the same wavelength. Okay, it's the fundamental. Okay, it's the fundamental. It's going to have the same tension. We're not tightening it. Okay, so what we have here is a relationship. Okay, between the frequency of the fundamental and the mass per unit length. So the frequency is inversely proportional to the root of mass per unit length. So you've got to see there, that's quite obvious that if you have a thicker string, we've got a higher mu. If we've got a higher mu, because it's on the denominator, we've got a lower frequency. So it'll be a lower pitch. Okay? 5 marks. Easy. Right. That was question 11. Next video, question 12.